Hello everyone, I am Dr. Osman reporting once again from the University of KwaZulu-Natal, South Africa, the premier university of African scholarship. Today we will be looking at energy balancing relevant to chemical engineering applications, of course. As you may know, depending on the chemical process you are dealing with, such processes may require very large energy inputs or very rapid and efficient harnessing of energy or its removal as well. Now, good knowledge of energy balances is required to optimize energy flow. Remember that energy input costs a lot of money, so it needs to be minimized. Energy output often gains money, so it needs to be efficiently harnessed as best we can. None of this can be achieved without a good understanding of energy balances. This is a second-year module, so some preliminary understanding is required from first year, and this will not be covered very thoroughly in these lectures, so I suggest you revise on previous knowledge. In this lecture, we will briefly recap on the different forms of energy and look at simple energy balancing for closed systems as well as open systems. We will then turn our attention to the use of water in industry for heating and cooling. We will recap the use of steam tables and address the issue of steam quality with some simple examples. So without further ado, let's get straight to it. Okay, so let's recap some definitions regarding energy balances. Okay, firstly, if we look at our system, a closed system is defined as such when there is no crossing of matter into or out of the system boundaries. Okay, so if we have a system containing any kind of process, let's say within this box, if there are no flows of matter into the system or out of the system, then it's a closed system. And of course, if there is matter crossing into and out of the boundaries of the system, then the system is an open system. Okay, and then let's look at properties which we can classify as extensive or intensive properties. Okay, so extensive properties are properties that are additive or proportional to the size of the system. For example, volume, mass, or energy. This is of course additive and dependent upon the amount or the scale of the system. Okay, so your mass will increase if you have more matter in your system, and same with your volume as well as your energy. Intensive properties, on the other hand, are independent of system size. Okay, so they will be unchanged whether the system is changed by a factor of 2, whether it is doubled in size or whether it is subdivided. These properties will remain the same. And examples of these properties include temperature, pressure, density, specific volume, and even things like concentration. Okay, so if you look at your can of Coke and if you look at a 2-liter bottle of Coke, the concentration of all of the ingredients are the same, so therefore your Coca-Cola will taste the same. Okay, so now let's look at our general principle for energy balancing. Our input of energy to the system from our surroundings is equal to the output of energy to the surroundings from the system plus the accumulation of energy within the system. Okay, so in other words, input is equal to output plus accumulation, or if we switch it around, input minus output is equal to accumulation. And typically at steady state conditions, accumulation will be 0. Okay, there'll be no accumulation. Under batch or semi-batch conditions, we will actually have an accumulation term. Okay, so now let's recap on the types of energy. We have firstly kinetic energy, okay, which is expressed as a half mv squared, where m is the mass of our substance, of our matter, and v is the velocity of our matter. Okay, so this is energy possessed by species by virtue of their movement, by the fact that they are moving, so they will have kinetic energy. Okay, and an example is flow through a pipe at an overall speed. Okay, then we have potential energy given by mgz, where m is the mass of our matter, g is the acceleration due to gravity, and z is the height above a datum point. Okay, now this energy is energy possessed by species due to their position. It's typically their height. However, it can also be a certain state, such as a spring that is compressed. It has a potential energy to expand, but typically potential energy is usually associated with height and gravity. Okay, then we have internal energy, which is energy that each matter possesses. Okay, it's inherent in the molecules of any substance. Okay, and this is due to their bond energy, their molecular vibrations and rotations. Okay, so that is the internal energy. That's classified as internal energy. And then we have heat energy. Heat energy is energy supplied by any heat source. Okay, in our context of chemical engineering, that heat source could ultimately stem from combustion of any fossil fuel, or it could be from microwaves or simple electric heating. Then we have work energy, which is typically mechanical work. Okay, it's also called shaft work, and this concerns compression, stirring, circulation, etc. Okay, now the absolute values of energy, of each type of energy, are often immaterial. We are typically interested in the changes in energy occurring in a system. Okay, the changes in energy will give us an idea as to how much of energy we need to remove to keep the system stable, or in other cases, how much of energy we need to add in order to keep the system stable and efficient. Okay, so we are concerned with changes in energy, and this could be absolute changes or a rate of change, with, in other words, a change over time. Okay, so for closed systems, and remember, closed systems have no mass coming into the system or out of the system, we have the following energy balance, where our changes in internal energy plus the changes in kinetic energy plus the changes in potential energy is equal to the heat transferred to the system minus the work done by the system. Okay, and there are many different conventions of this. In this particular case, we are looking at the convention of Q being positive if heat is added to the system and negative if the heat is removed. And our work, W, is positive if work is done by the system and negative if work is done on the system. Okay, so there are different ways of writing this out, different conventions, where you will perhaps read in certain textbooks we have this left hand side being equal to Q plus W, and in this case our W will be positive if work is done on the system and negative if work is done by the system. Okay, so take note of your convention, okay, and work with it accordingly. Okay, it's quite fine to use an alternative convention of Q plus W as long as you are consistent in your approach. Okay, so this is just a simple diagram of a system that's closed. Okay, so we have in our system, we have kinetic energy, potential energy, and internal energy. And remember, our kinetic energy is equal to half mv squared, where m is a fixed mass. There's no mass going in or going out. The potential energy is mgz, Okay, again a fixed mass, and then we have our internal energy, also dependent upon the mass. Okay, and then we have our work coming in from the surroundings to our system, and we have energy coming in, and then we have work leaving the system to the surroundings. Now, this is the expression in absolute terms. If we want to express it in rate terms, okay, over a certain time period, we get the following. Okay, so we have ddt of our internal plus potential plus kinetic energy, and that is representative of the rate of accumulation of energy, and that is equal to our output minus our input. Okay, so dq dt is the rate of energy input, and dw dt becomes representative of the rate of energy output. Okay, so this is for closed systems. Now, if we look at open systems, we have our energy input and our work output, and we have streams entering and leaving the system, and this is typically what we've looked at from a material balance point of view all along. Okay, so in practice for open systems, calculations for chemical engineering applications, we have to consider the internal energy as well as the work done to and by the system to push material through the system. So we can group up these terms and define enthalpy, okay, H with a cap, as follows. So we have H is equal to U plus PV. Okay, so remember that we have for open systems, some work had to have been done to actually push our material into the system, and the same amount of work will be done to push that work out of the system. Push that material out of the system. Okay, so that is what we are talking about here. And of course, with our matter coming in, that matter will have an internal energy coming in, and it will have the associated internal energy coming out. And for this reason, we can actually group up these terms into an enthalpy term. Okay, and as you may notice, all of these things have a little cap there, and this is to denote specific. Okay, so we have specific enthalpy, specific internal energy, and specific volume. Okay, by specific I mean that we are talking about the enthalpy per unit mass of components entering or leaving the system. So it's an enthalpy per unit mass. The specific internal energy is internal energy per unit mass. And here we have our PV, which represents the work done to and by the system to transport the components through the system. Okay, so that's our enthalpy term, and if we expand on our equation for closed systems and extend it to open systems, we get the following. Okay, so we have our input minus output must equal to accumulation. Okay, so take note of this. We have our accumulation, and then we have input minus output. In this case, our input is not only the dq dt but also the material coming in. Okay, so this entire term here represents the energy associated with our material coming in at stream 1. Okay, so it will have an associated internal energy, a work energy as a result of its flow. Okay, some work had to have been done to push that fluid into the system, as well as potential energy and kinetic energy. Okay, and then we have, in addition to our output, okay, so remember for closed systems we have our rate of energy output, being represented only by our work in this case. But for open systems, we have our output represented in terms of our stream 2 flowing out, okay, with its associated internal work energy, its potential energy, as well as kinetic energy. Okay, so we have an input dq dt as well as stream 1 input, and we have our output being our stream 2 flow out, and also this term here dw dash dt. Okay, and this is different from our standard dw dt because dw dash dt represents all of the system work excluding our flow work. Okay, so remember our work over here consists of a variety of types of work. It could be our pumping of our fluid into and out of our system. It could also be compression, it could be turbines or stirring mechanisms. All of that is lumped up as work. But now for open systems, we are taking out our pumping work term. Okay, so in other words, our flow work, and we are writing it here in terms of P1 V1 and P2 V2. So therefore we have this dw dash dt, which represents all of the other types of work. Okay, so this could include our shaft work, our stirring, compression or driving of turbines. Okay, so any other type of work excluding our flow work. Okay, and this is of course once again equal to the rate of accumulation of energy in the system. Okay, and that's again given by the following. And note that at steady state, this whole term here will of course become 0. So to write this out once again in enthalpy terms, so we are grouping up our U plus PV, and we obtain the following general equation, which is perhaps the most important equation which you will be using for energy balancing. Okay, so we have our input of energy minus our output, rather our inputs of our input streams here and the dq dt, as well as our outputs. Okay, so if we group up our enthalpy terms, H is equal to U plus PV. So instead of having the internal and flow work energy, we are grouping it up to form our enthalpies for our input stream and our output stream. Then for steady state, remember accumulation is 0. So this large equation here ultimately becomes the following. Okay, and we can group up our streams on one end and our actual energy inputs and work outputs at the other end. Okay, and this is the most general energy balance equation for steady state open systems with multiple streams. Okay, so we are writing this in terms of a summation. Okay, we may have multiple input streams and multiple output streams to our system, not simply just a single input and output stream. So we have to include a summation, and each stream will of course have an associated flow rate. Okay, so that's our flow rate there, a mass flow rate. Okay, now remember before that the dw dash dt represents all of our work excluding flow work. Okay, so from now on I'm just going to drop off this dash, and I'm just going to say dw dt is going to equal to the rate of change of all work excluding flow work. Okay, so that's just an understanding that we're going to have from now on when we are talking about our work. Okay, and note that enthalpy is a state function. Okay, so what do I mean by a state function? It means that enthalpy in and of itself has no absolute value. Okay, so if we talk about the enthalpy of any substance, we don't really know what the absolute value is. Okay, it's typically defined against a reference. Okay, so whenever we talk about enthalpy, if the enthalpy of, for example, gasoline is 200, then it means that our enthalpy is 200 times more than that of a reference point. And in this case, we often define our reference point to be water at triple point conditions. Okay, so whenever we are talking about enthalpy, remember, there is no absolute value of enthalpy. Every kind of enthalpy of any substance, whenever it has a value, that value is simply a value expressed against the reference point of the enthalpy of water at triple point. So we set as our datum point that the triple point of water has an enthalpy of 0. And anything above that is of course compared to this point. Okay, so now that we know about our energy balance, let's look at what it means for our non-reacting systems. Okay, firstly we can note our phase rule or our degree of freedom analysis. Degree of freedom is equal to the number of components in our system minus our number of phases plus 2. Okay, so C is number of components and phi is number of phases. Note that if we have a single component, just one component, then C is of course 1. And our degree of freedom is equal to 3 minus phi. Now our degree of freedom in case of our energy balancing can never be negative. So for a single component system, if our D is equal to 3 minus phi, then it means that phi can be a maximum of 3. Okay, so we can have up to a maximum of 3 phases. And this 3 phases typically occurs at triple point, and we'll talk a bit more about triple point as we go along. Okay, so if we look at a typical pure component phase diagram, okay, of pressure and temperature, we typically have the following lines, okay, and that will separate our solid, liquid and vapor phase. And as you can see at this point here, known as the triple point, at this particular temperature and pressure, our pure component will exist in 3 phases. Okay, so that is the maximum phases that a component can exist. And then we can also, at any other point, of course, we will have our component existing either in the solid, liquid or vapor phase. And there are of course various lines or various equations to describe these lines, one of which is the vapor pressure curve for liquid to vapor transition. Okay, this is also known as the Anton equation, with associated Anton coefficients unique to each component or each type of compound or molecule. Okay, and note that if a component is in a single phase, in other words not on the triple point, then with phase being 1, our degree of freedom will be 2. And this means that any 2 of pressure, temperature or volume will need to be known in order to fix the third. Okay, typically using an equation of state. So if we consider, for example, the ideal gas equation, if we know pressure and temperature, we can calculate volume. Or if we know pressure and volume, we can find temperature, etc. For non-ideal conditions, we can use a more real equation of state, such as the van der Waals or any other higher order equation of state. Okay, and this is the case for a single component, one component in one phase. If we have to look at multi-component systems, then simply knowing the pressure and volume will not give us all of our information, because with multi-component systems we need to know what our composition is as well. So if we know, for example, pressure, temperature and composition, we can obtain our volume. Or if we know pressure, temperature and volume, we could perhaps obtain our phase composition. Okay, and this is the subject of thermodynamics, which you will study in the future, in future modules. But for now, what does the degree of freedom analysis have to do with enthalpy and our energy balance? Well, we can, of course, obtain various relationships between our pressure, temperature and enthalpy in order to determine our points of phase transition and our associated enthalpy required to accomplish these phase transitions. Okay, so this particular page that you're looking at is a pressure enthalpy diagram for propylene. It's of course not very clear, so I'm going to actually just draw up a more simplified diagram. So if we consider our pressure and our enthalpy, we have the following type of phase transition. We have a saturated region, okay, and this will consist of, okay, I'm going to just mark this in blue here, and this is my saturated liquid line. Okay, and then I have a saturated vapor line. And now this is a pressure and enthalpy diagram, so I need to be able to relate my temperature as well. And we could relate it as follows. We can draw out our isotherms. Okay, so these are my temperature isotherms. Okay, I'm just going to draw a few just to show you the form, and then we can explain it later. Okay, and these would be, for example, 0 degrees, 10 degrees, 20 degrees, 30 degrees, etc. Okay, so what is this diagram actually explaining? Okay, so this diagram explains the mechanism of phase transition. So if we look to the left of our saturated liquid line, this region here will be the subcooled region. Okay, so this is subcooled, and as you can see, for any particular isotherm such as 0 degrees, or let's look at 10 degrees, we note that as our compounds gain more enthalpy or more energy, let's say for example if I want to heat from 0 degrees to 10 degrees at this particular pressure, then we require a certain amount of energy, a certain amount of enthalpy to increase from 0 degrees to 10 degrees. However, let's look at the pattern of our isotherms. So once we are at 10 degrees, let's say if I want to heat further and add on more energy, then what's going to happen? Okay, now since our isotherm is leading down here right to our saturated liquid line, so we ultimately, as we are increasing in enthalpy, we should notice a pressure drop. And note that within this saturated region, my temperature is actually constant. It's a flat line because our phase transition occurs at constant temperature and constant pressure. Okay, so if we heat up any further, then we will end up in this region, and if we want to completely vaporize our compound, we need to provide it with enough enthalpy to get beyond the saturated vapor line. Okay, so in this particular region here, we will have a mixture of liquid and vapor. To the left of the saturated line, there is a subcooled region where all of the compound is a liquid, and beyond the saturated vapor line we have our superheated vapor. Okay, and this occurs for various temperatures, and then of course we get to a point where this dome is actually no longer valid, and we have a temperature where we just are touching or skimming the top of this globe. Now this particular point here represents the critical point, and as you can see, as we increase in our temperature, there's actually there's nothing to distinguish between liquid and vapor. And if you look at our phase diagram, this point here actually represents this critical point here. And so if we go and increase our temperature further, we won't be able to distinguish between liquid and vapor. Okay, another thing of note is that, as you can see, we require quite a small amount of enthalpy to heat up our compound from, let's say, 0 degrees to 10 degrees. However, if we wanted to convert our compound from a subcooled liquid to a superheated vapor, the energy difference is very large. Okay, and if we look at comparative values for water and other chemicals, you will note the very large difference. Okay, so if we have to heat up a compound, for example, from 0 degrees up till maybe, let's say, 50 degrees, what would actually happen? Okay, so if we are heating, let's say if I want to operate here and keep the pressure constant, we will have a sensible heat to heat up our liquid from 0 degrees to 10 degrees. Okay, so that will be known as sensible heat, where we are just heating a liquid. There's no phase change. And then we have to heat up to account for the phase transition. Okay, so this is known as our latent heat. And this occurs at constant temperature and pressure. Thereafter, we require more sensible heat to go from a saturated vapor to a superheated gas at 50 degrees. Okay, so that's sensible heat here, latent heat, and sensible heat here in the gaseous phase. Okay, and as you will note as we go along, we will have different enthalpies to deal with. The enthalpy of vaporization deals with our latent heat, and our sensible heat will be dealt with using specific heat capacities. Okay, and we will look at that as we go along. Okay, and now we're going to talk about the use of tabulated data tabulated thermodynamic data does exist for various popular compounds, and we will look at how we can use thermodynamic data to solve energy balance problems. Okay, so let's revisit our steady state open system equation. Okay, so where we have our inputs minus our outputs equal to accumulation, and at steady state, of course, accumulation is 0. Okay, and simply shifting around our terms for our input flow and our output flow, as well as our energy input and work output, we get the following expression. Now, typically for chemical engineering purposes, potential and kinetic energy are often quite negligible or often non-existent, or alternatively quite easy to calculate. However, it is our enthalpy, our state variable here, in our input and output that can be significantly more difficult and more tedious to calculate. Now, in the case of water, our specific enthalpy, specific internal energy, and specific volume is abundantly studied, and data is tabulated for various pressures and temperatures. Okay, you must know that water is, of course, the most abundant chemical on our planet, so it is quite sensible to expect that it is the most studied compound. Okay, so water is abundant, it's cheap, and also non-hazardous. And for this reason, it has particular uses, well, various abundant uses. In the context of a chemical plant, water can be used as a solvent, for dilution, for, of course, purification or washing, or for heating or cooling in many industries. Okay, so if we look at a general setup of a chemical plant, a factory, which utilizes water for heating and cooling purposes, we typically have, this is our chemical plant here. Let me try and use some colors. Okay, so this is our chemical plant. And we typically have a water supply, and this water supply ultimately supplies cooling water as well as steam. Okay, so that's our water supply. Let's look at our steam cycle. We have water from the water supply coming in, so this is actually cold water, and it goes to a boiler where the water is converted into steam. Okay, and thereafter we have our steam being used in various parts of the plant. And as you know, once the steam is being used to heat something, the steam itself is actually getting cooled, so it needs to be recycled back to the boiler. In the case of steam losses, which may occur in our plant, we need to top it up once again with our water supply. Okay, so that's our steam cycle. Now if we look at our cooling water cycle, we have water from our water supply, and it is being used all over in our chemical plant wherever it is needed to cool down certain units. Okay, it could be needed as a cooling medium for exothermic reactors or various other processes as well. Okay, and of course, once the water is being used to cool a unit, the water itself is being heated up. So the water needs to go to a cooling tower to become cool again, of course, and then it is resupplied back into the water supply. Okay, so that's the basic setup. There are, of course, many different variations of this, as well as different heat interchanges as well. So, but I hope this gives you a general sense of how water can be used as a heating or cooling medium. Now, as mentioned, data is quite abundantly available, and it's available in order to cater for our subcooled region of water, for our saturated region, as well as our superheated vapor region of water. Okay, so let's look at a saturated steam table, and this is expressed in terms of temperature. So this steam table here in particular concerns the saturated region of our pressure enthalpy diagram. Okay, you've seen this before. I've done this in color, but this is the saturated region that we were talking about. And as you can see, for each temperature we have an associated vapor pressure. Okay, so this is the pressure required to keep our liquid water a liquid. Once we pass this pressure, we will of course obtain water in the form of vapor. Okay, so this is at saturated conditions, saturated pressures and temperatures, and this is for various temperatures with an associated pressure. And we are typically given our specific volume, our specific internal energy, and our specific enthalpy, and we are given this in terms of saturated liquid and saturated vapor. And as you can see, in the case of specific volume, we have a very low volume for liquid water, saturated liquid, but once it becomes saturated vapor, there is of course a significant volume expansion. Okay, and again for the internal energy as well as the specific enthalpy, you see we have a very low energy for saturated liquid and a comparatively very high energy for saturated vapor. Okay, and this is the same for our liquid water here for our enthalpy. Very low enthalpy values. Remember, our enthalpy values are expressed by comparing water at triple point. Okay, and so here is our water at triple point. Okay, at 0.01 degrees. That is the common expression. Okay, there are other steam tables that can express our steam in other relative to other conditions. So it's important when you are using steam tables to actually use the same table for all of your calculations, because all of these values are referenced to a certain 0 point. Okay, so in this case we are looking at temperature of 0 degrees for water. Other tables could use triple point as the reference. Now back to our enthalpy, and as you can see, we have very low enthalpy values for our liquid water, our saturated liquid, and comparatively very high values for our saturated vapor. Okay, and this was discussed graphically when we saw a very large enthalpy difference between our saturated liquid and vapor. Okay, so that's our saturated table, and it is expressed in terms of temperature here. We can also express it in terms of pressure. So if we have our pressure, we can find our saturated temperature. Okay, so this is a saturated steam table. This is the pressure table. Okay, and it's providing, of course, the same values. Okay, so the tables that you've just seen concern our saturated region. But what about our subcooled region and our superheated vapor region? Okay, for that we need to look at subcooled and superheated steam tables. And this is just a small part of the actual superheated steam table. So properties of superheated steam. And as you can see, for each pressure, so we have at 0 bar, 0.1, 0.5, 10, 20, 40 bar, and above that we can obtain as well. And as you can see, for each pressure we have the associated saturated temperature being stated in our brackets here. Okay, and for each pressure we have various temperatures from 50 to 350, and the table of course extends to more than 350 degrees. Okay, so if we take for example a pressure of 1 bar, and if we are concerned with water at 200 degrees, we can obtain our enthalpy, our internal energy, and our specific volume. Okay, so that is why we have 3 rows here for each pressure. Okay, and what this tells us, notice that we have this little block barrier here separating, and what this tells us here is if our pressure is 1 bar and if we are operating at 200 degrees and we are outside this block barrier, then we are actually dealing with superheated vapor. Okay, so we are dealing with this region here. Now anything inside this block bar actually deals with our subcooled region. Okay, and as you can see, the differences in enthalpy and internal energy, etc., are all significantly lower for our subcooled region. And one important thing to note is that this diagram takes into account our latent heat of vaporization. So if I were heating a liquid, for example, from 50 degrees to 200 degrees, I can simply note the difference in my enthalpies. Okay, so we don't have to look at dividing into sensible heat, latent heat, and sensible heat again. The sensible heat is already included in our difference. Okay, and that's the advantage of using our steam tables if they are available. Okay, now if we are faced with a certain circumstance where we need to obtain information at temperatures that are not on this table, let's say for example 130 degrees, then we need to simply interpolate between our enthalpies at 100 and 150. We can also do the same for our pressures. If we want information for 3 bars, at a pressure of 3 bar, we'll need to interpolate between our enthalpies at 5 bar and 1 bar. Okay, so let's say if we're looking at 250 degrees, we'll have to interpolate between these two. Okay, and there may be circumstances where we need to interpolate for our temperature as well as our pressure. Okay, which is a tedious but a relatively simple task. Okay, just simply using the interpolation equation. Okay, which we can easily express here. Remember, when we interpolate, we are assuming that since we are working over such a narrow range, we can apply the straight line equation. So this is our interpolation formula for obtaining, for example, enthalpy or specific volume or internal energy at any internal temperature or pressure. And we have our 2 bounds which we actually know. Okay, or y2, y1, x2 and x1. Okay, and there will be some examples that require interpolation which you can practice on if you are in the mass and energy balance class at UKZN. Okay, and now on to another topic, and that is the topic of steam quality. The factor of steam quality. And steam quality deals with the saturated region once again. Okay, so remember we have our saturated region, and we have our saturated liquid line and our saturated vapor line. And remember that in between here, we can expect to have a mixture of vapor and liquid occurring. However, since there is such a large difference between the saturated liquid and saturated vapor, we can actually infer that as we are nearer to the saturated liquid line, we will of course have more liquid than vapor. And as we progress to the saturated vapor line, we will obtain more vapor than actual liquid. And once we are at the saturated vapor line, there will only be vapor. Okay, but what if we are indeed operating at the saturated point and we do have a case where we are using neither saturated liquid nor saturated vapor? Okay, and this is the common case when we try to generate steam, however we don't have enough energy. So we end up creating what is called wet steam, and that wet steam consists of liquid and vapor, and it's useful to quantify how much of liquid and how much of vapor. Okay, and this is what steam quality is about. Okay, so sometimes steam may get partially condensed or even partially vaporized, so that we end up having a mixture of saturated steam and entrained saturated liquid. Okay, so the steam is then called wet steam. Now we define our steam quality, denoted by X, to be the mass fraction of vapor in a mixture of liquid and steam, or in other words liquid and vapor. So we're looking at the mass fraction of our vapor. Now if X is 1, then we can expect to have entirely saturated vapor, so all of our water will occur in the vapor phase. However, if X is 0, then we can expect to have saturated liquid. But if X is in between 0 and 1, then we have a mixture of vapor and liquid, and this is known as wet steam. Okay, anything above this, of course, above the saturated vapor, is of course dry steam. Okay, that doesn't have any liquid water. So we can obtain our exact enthalpy, internal energy and specific volume within this region here, okay, within this region, by expressing it in terms of our steam quality. So if we have wet steam with a particular steam quality, we can obtain our enthalpies, our internal energy and specific volume. Okay, so our enthalpy, for example, is equal to the enthalpy of the saturated vapor multiplied by our X, our steam quality, plus the enthalpy of saturated liquid times 1 minus our steam quality. Okay, and it's a similar equation for our internal energy and our specific volume. Okay, so this is our mixture enthalpies, etc. in terms of X. We can also write X in terms of our mixture enthalpies here. Where X is equal to H mix minus the saturated liquid enthalpy over the difference between our saturated vapor and saturated liquid. We can also express X in the same way in terms of internal energy and specific volume. So let's look at an example. Find the pressure, specific volume, enthalpy and internal energy of a wet steam at 230 degrees with a quality of 0.4. Okay, now the fact that they are telling us that it is wet steam already implies that we are talking about the saturation point. And since they've given us 230 degrees, we can quite immediately find our pressure. Okay, so let me just zoom in a bit. Okay, so at a temperature here of 230 degrees, we can immediately determine our pressure to be 28 bar. We can also obtain all of our other information. Okay, remember we have our specific volume, internal energy, and specific enthalpy for saturated liquid and vapor for each. So we can immediately obtain, this is our VL and VV, this is UL and UV, and this is our HL and HV. Okay, so I've noted it down here, and since they've given us a steam quality of 0.4, I can quite easily use the equation to obtain all of my values for my mixture, for my wet steam. Okay, and that's the problem solved. Let's look at another example. Okay, and this seems like a simple example. We have a pressure vessel and we are given the volume of that vessel, and it contains 10 kgs of water at 60 bar, and we want to know its enthalpy. Okay, so they've given us the volume and they've told us it's 10 kgs of water, so we can immediately find our specific volume. So this is our specific volume, and at this point, although over here I've called it V mix, I actually don't really know whether we are talking about the saturation point or not. Okay, so we can simply look at the fact that we have been given 60 bars and 0.3 meter cubed for 10 kgs, so we only really have our pressure and our specific volume to work with. So let's look at our superheated steam table, or rather our saturated table first. Let's see if we are operating at the saturated region. If we are not, then of course we will be either in the superheated or subcooled region. Okay, so looking at our saturated steam table, at 60 bar we have the following information, and okay, so this is our specific volume for water and steam, and remember that the specific volume that we calculated was 0.03, and currently here we have our VL being 0.0013 and our V for the vapor is 0.0324. So our specific volume seems to be lying between the saturated liquid and saturated vapor region. So we are definitely dealing with wet steam. Okay, so now that we've established that, we can use these values to actually calculate our steam quality. So we have our V mix, and from our steam tables we could obtain our V for our vapor and liquid phase, and thereafter calculate our steam quality quite easily. Okay, and what this implies is that we have 92.3% vapor and 7.7% liquid. And thereafter we can use the same information at our steam tables for our enthalpies. Okay, so that's for our saturated liquid and saturated vapor, and we can use that to calculate our enthalpy of our wet steam, of our mixture. Okay, now let's look at a simple energy balance example where we can use our steam tables. Okay, so consider the following heat exchanger where we have water coming in and it's being heated up from 50 degrees to 150 degrees by saturated steam. Okay, so saturated steam comes in at 10 bar, and we have saturated condensate coming out at 10 bar. So effectively, the saturated vapor is giving off its latent heat and becoming saturated liquid as the output. Okay, and we are given a mass flow rate for the water, and also we have 5 bar water coming in and water coming out as well. Okay, now it's quite obvious that F1 will equal to F3, the mass flow rate, and F2 will equal to F4. Okay, there's no actual mixing occurring, it's simply energy transfer from the saturated steam to the water. So let's consider our energy balance. Okay, and we want to of course find the required steam flow. Okay, so this is what we require, our Fs or F1. Okay, so considering our inputs and our outputs, we have our input streams, which is the water coming in as well as our saturated steam coming in, and we have our output streams, water coming out and saturated condensate coming out. There is no mention of any further heat input, so we can assume dq dt is equal to 0, and no mention of any shaft work or any stirring or compressing, so we can assume dw dt is also equal to 0. There's also no mention as to whether the steam is wet steam. There's no mention of any steam quality, so we can also assume that we have a steam quality of 1, so perfect saturated vapor coming in and perfect saturated condensate going out. And making these following assumptions, also there's no mention of kinetic energy or potential energy changes, so we can assume that these are 0 as well. So we simply have our energy coming in due to flow, and that's equal to our energy out due to flow. And if we expand this, we have H1 F1 plus H2 times 3000. Okay, we know the mass flow rate, and that's equal to H3 times F1 plus H4 times 3000. Okay, F3 is of course equal to F1 and F4 is equal to F2. So we are assuming a steam quality of 1. So how do we solve this problem? Okay, since we are working only with water, so we can actually use steam tables for everything because we are working with water and with steam. So let's firstly look at the saturated steam coming in and then giving off its latent heat to become saturated condensate. We are given the saturation pressure of 10 bar. So we can ultimately look at our saturated steam table. Okay, and this is at 10 bar. And we look at our specific enthalpies, and we have our enthalpy of our saturated condensate and saturated vapor. So if we go down here, and these are the values at 10 bar. So we can assume that the specific enthalpy of our saturated steam coming in is 2776.2 kilojoules per kg, and it is going out at 762.6 kilojoules per kg. Okay, so that's one valuable piece of information we can obtain from our steam input and our steam output. Regarding our water coming in and going out, we have water at 5 bar and 50 degrees. Okay, it's unlikely to be saturated. They've given us the pressure and the temperature. So we can immediately look at our superheated steam tables. Superheated and subcooled steam tables. Okay, and if this is at saturation conditions, then our our study of our superheated and subcooled steam tables would reveal this. But for now, let's look at trying to find water at 5 bar at 50 degrees. Okay, so here's my superheated steam table, and I can check for 5 bar and 50 degrees. So I have a specific enthalpy of 209.7 kilojoules per kg once again. And remember that my output is water at 5 bar and 150 degrees. So I can look for 5 bar and 150 degrees. Okay, and this reveals that my specific enthalpy is 632.2. So our water actually remains in the subcooled region. It remains as liquid water. Now if it vaporized, it wouldn't be a problem. We could simply look at our higher temperatures, whatever the temperature is, and perform the same calculation. Okay, and this is the convenience of using steam tables. We simply need to look at our input and our output. We don't have to consider our sensible heat, latent heat, and sensible heat in our gaseous phase separately. Our latent heat is in fact included in our superheated steam tables. Okay, so if the water actually vaporized, if the temperature was higher, it wouldn't be a problem. But for now, we are looking at 50 to 150, so we can look at these two values. Okay, so here's my H1 and H3 retrieved at 10 bar using my saturated steam table. And here is H2 and H4 in specific terms, as found as 209.7 and 632.2 using the superheated and subcooled steam table. And thereafter, it's simply a case of substituting these specific enthalpies into this energy balance equation to ultimately obtain my F1, which is equal to F3. Okay, and we get the following result. Okay, and finally, some final points. Okay, so that's the problem solved. So just some last points to note. Thermodynamic tables do exist for a few other compounds. So we don't only have steam tables for water. We have steam tables for other popular compounds such as benzene, ammonia, various refrigerants, and even nitrogen gas. Okay, and all of these tables are used in the same manner. There's nothing different about them really. Okay, and as you've seen in the previous example, if a problem doesn't mention one or more types of energy, you may assume that it's negligible and you can neglect it. Okay, as we have done in this example. Okay, so that's the problem solved using steam tables.